Good afternoon, Bipul sir.
Good, good afternoon, sir.
Good
How are
afternoon. How are you? How are you, sir?
I'm good, I'm good.
Okay. Good afternoon, all the participants and Bipul sir. Uh, Today, this is the fifth day of the machine learning and pattern recognition. So, Mr. Bipul Kumar sir is present with us for continuation of the session. So, I am handovering the session to the Bipul sir. Thank you, sir.
Thanks a lot, sir. Okay, hi everyone. Very good afternoon. So what we did till now and how we're going to proceed, let me share my screen first. Okay. So what we have covered means as per my sessions, okay, we have discussed some important machine learning techniques and terms. Okay, those are very, you can say, grassroots level things. Okay, those concepts needs to be very clear. Okay, if we want to create a better model, like a better accurate model, better performing machine learning model. Okay, so we started our journey with a data science things. We understood about data science part. Okay, as per my session, I am considering my session only. Okay, then we had understood about the classification thing, that was under classification, that was considered under what, supervised learning. Then we had understood regression. Okay, that was considered under again supervised learning. Then we had gone through the part of clustering. Okay, that is under unsupervised learning, right? Now today we have to discuss about the PCA, or principal component analysis, or dimensionality reduction. With both are same thing, dimensionality reduction. Okay, that is also a kind of a unsupervised learning approach, correct? So whatever we have discussed till now, I hope it is clear to all of you. If you're having any doubts regarding it that I had covered till now, please just let me know. Okay, please, you can just let me know. I will try to clear your doubts. Today we are going for a dimensionality reduction. Shall we proceed with dimensionality reduction? Will it be okay? Yeah, you can just let me know. Shall we proceed with dimensionality reduction, or anything that you want to ask? Yes, no, anything. You can just let me know, right? Anyway, I hope it is yes from your side. Anyway, if you are having any doubts, please do let me know. I will definitely try to answer. Okay. So dimension reduction is what? Look here. It is reducing the high dimension data basically, right? For example, you are having a data in, there are so many features. Okay, F1, F2, F3, F4, okay, F5, F6, F7, F8. There are so many features are there. Okay. So what it is expected, and there is one label. Okay, so basically if we are using high number of features, that means it will be like so many features leads to the kind of a so much calculation, so much processings, isn't it? For example, if it was like if you're having, if 2 plus 3, if I have to do this thing, I can do it very easily, isn't it? At the same time, if I have to do like 22 plus 79 plus 39, okay, it will take a little time from for me, right? Same thing happen with a machine, right? If we are using a heavy sets of feature, machine will take a little more time to process the things and create the model, correct? So it was thought that can we reduce the number of features in less number of sets, okay? And from there, or you can reduce the size of features, can we reduce the dimension of features, okay? And from there it was thought of reducing the dimensions, okay? That means by combining the information of all these dimensions, by combining the information of all these features, we can generate a less number of features like fx1 and fx2. Okay, this fx1 and fx2 can represent all of these features with a maximum information. That means almost suppose 90% of information. Okay, if 90% of the information is present in fx1 and fx2, okay, 90% of the information that was present in f1, f2, f3, f4, f5, okay, that means our job is done. That means to train our model, we can use fx1 and fx2 only. Okay, instead of using all these things. Correct. In that case, if we are using these two value for training our model along with the label, then obviously training will be done quickly. And on the ground of prediction, it will also do the predictions quickly. Right. So there are so many benefit of it. Okay. So that is why dimensity reduction or PCA was thought of. PCA, principal component analysis, or dimensionality reduction. Okay. Now we have to understand it, how it works. Correct. So let's start from the very beginning, like from the starting. Like whenever I start from the very first point from where all these things happens. Okay. Because for doing it, it is just 3 lines of code. Okay, like you had seen earlier also. For linear regression, it was just 2 or 3 lines of code. For classification, it is just 2 or 3 lines of code. For k-means, it was just 2 or 3 lines of code. But again, the concept is not of two or 3 lines, right? The mathematical concept is always going to be so much things. So much thing needs to be considered, right? So ultimately, we should understand the mathematical concept, because suppose if tomorrow Python will not be there, then if suppose we are switching to some other language, okay, so we can use any language if we know the concept. But if we just know how to use library, then we can only use that particular language. Okay, that means we can only use Python. Okay, if Python will not be there, well, like tomorrow, industry is not requiring any more Python. Python is getting outdated. Things gets outdated. Okay, if Python gets outdated, then what we will do? Okay, today Python is in the use, so we can use Python. But suppose tomorrow if Python gets outdated, then what we will do? Okay, but if we know the concept, okay, we can use anything, any language, any other things can be used, right? So the concept is very important, right? So what we have to do, we have to first understand how the process starts. The first understanding of mean is required. Okay, what is mean basically? Correct. So mean is basically suppose there is any value, okay, 88, 34, some value, just I'm giving 56, 73, and 62. Okay, suppose these are the values. So what will be the mean? The mean will be this one, 62.6. Now you may ask why I am talking about the means, okay, mean of feature. Okay, because if we know the mean, then we can easily calculate something that is known as variance. Okay, variance we have to calculate. Okay, now we have to figure out, now the thing is why we should go with the variance part. So let me tell you, variance is very important in this discussion. Correct, because we have to understand covariance later on. So what will be the variance? Variance will be 88 minus 62.6 whole square. Okay, that means 88 minus 62.6 whole square plus 34 minus 62.6 whole square plus 56 minus 62.6 whole square, okay, plus 73 minus 62.6 whole square, right? Just a minute. Okay, got it. Plus 62 minus 62.6 whole square. Okay, this is called variance. I will tell you the use of this. Okay, first of all, I am just giving the concept of it. Divide by 5. Okay, so this will be around 323. I have already calculated, that's why I'm using it so that I can explain quickly. 323.04. Okay, so it is a variance. So what does the variance mean? Okay, how is variance helpful? Okay, so the variance basically used to calculate something called a standard deviation. Okay, a standard deviation. What is the standard deviation? Standard deviation will be under root 323.04. That will be equal to 17.97. Okay, so it is your standard deviation. Okay, now how standard deviation can be used? Basically, a standard deviation is used in a data to figure out the outliers. Okay, the values which are not common. Which are not common means what? The value which are not often. Those values which are not occurring very often. That means they are occurring very rare. Okay, that means what? You can see, if you see the value over here, what is mean? Mean over here is 62.6. Correct. Now do two things. First, plus 17.97, and second, minus 17.97. Right. So if you do plus 17.97, what will you get? you will get a value. If you add it, then what will you get? 17.97. If you add it, just add, and if you can tell me, please tell me. Otherwise, I will calculate. I have not calculated it. 62.6 plus 17.97. What I'm getting? 80.51. Okay, 80.51. The value is what? 80.51. Correct. And if I will do the subtraction, 44.69. So what it means? 44.69. It means if you see the value, the first value is not within the first standard deviation. It is 88, somewhere over here. The second value is 34. It is somewhere below over here. Okay, but rest all the values are within this particular range. Okay, so that means if you are having any feature, okay, and that feature is somehow repeated, because machine learning, those features will be there. Okay, so we will use only the actual some meaningful feature. Okay, so through this particular process, what we can do, we can calculate the standard deviation. Okay, and the standard deviation tells us that what are the features which are most likely and what are the features which are less likely. Okay, so that means only less number of features will be less likely. The feature which is outside the standard deviation, okay, the features which are outside standard deviation will always be less likely. Okay, the features which are outside what standard deviation will always be what? Less likely. Correct. So that's how we can say that these are the features which are occurring very less in number. Okay, these are not most common, so they can be ignored. Okay, they can be what? They can be just ignored. Okay, they can be just removed. Okay, to for the betterment of your model. Correct. Thereafter, so once we calculated a standard score, okay, sorry, standard deviation, we calculate something that is known as standard score. Okay, we calculate something that is known as standard score. Now, what is standard score basically? Right. So we have to just check it out. What is standard score? So let me remove it. Okay. And let me tell you what is standard score. Okay, because standard score will tell us the complete story. Whatever story that we have created over here, this whole story will be told by standard score. Right. So let me tell you the let me tell you the standard score. Actually, I don't know why camera gets okay. So what is standard score? Basically the combination of everything. You will see this thing so many times. Z is equal to, Z is standard score, x minus mu upon a standard deviation. What is Z? Z is a standard score. What is x? X is the value. What is mu? Mu is your mean, and this is your standard deviation. This is your mean, and this is your standard deviation. Standard deviation. Correct. This is your standard deviation. Okay, let's take an example to understand. Okay, now suppose there is a condition where some students had given the exam and they got the result like this. Someone got result 22 marks, someone got 17 marks, someone got 28 marks, someone got 30 marks, someone got 20 marks, someone got 26 marks, someone got 37 marks, someone got 16 marks, someone got 26 marks, someone got 22, and someone got 19 marks. Right. Now these are the students. Right. Now you have to decide who pass the exam and who fails the exam. Okay, then what we will do? Obviously, we can say that all the students who got less than 25 marks will fail. In that case, most of them will fail. Okay, if I say all the students who got less than 30 marks, then all will fail. Okay, so in that case, most of them will fail. Okay, so in these kind of cases, what we do, we go with something that is going to most likely. Most likely means what? What are the range in which most of the students are basically lying? Okay, what are the range in which most of the students are basically lying? So what we can do, we can calculate certain things that are known as mean of it. Okay, so if we calculate the mean, you will get the mean is equal to 24. Okay, and if you calculate a standard deviation, you know what is standard deviation? I told you a moment back. Okay, root over variance. Okay, root over variance is a standard deviation. Correct. So standard deviation will be around 5.96. Correct. Now, according to formula, the Z score we can calculate one by one. So for the first one, Z score will be what? 22 minus 24 upon 5.96. This will be equal to what? 0.33 minus 0.33. Okay, the same way you can calculate the standard score for all of them. Okay, all of them, 1 2 3 4, like that. Okay, for all of them, correct. So if you calculate the standard score for all of them, you'll get the values like this: minus 1.17, okay, 0.67, okay, 1.00, okay, minus 0.67, okay, 0.33, right? Thereafter, what? 2.18, okay, minus 1.34, okay, 0.33, okay, and minus 0.33, then minus 0.83. Okay, these are the values, right? So what these values are representing? These values are representing what are the points which are lying under first standard deviation and what are the points lying under second standard deviation. That means all these points: 0.67, 0. Minus 0.67, minus 0.33, okay, minus 0.83, minus 0.33, okay, 0.33, okay. These are the points which are lying under first standard deviation. Okay, you can see the first point 22, the second point is not, the third point 0.67, fourth point 0. This one, okay, okay, and then this one, okay, then this one, last three, right? Last three, this one, and this one, okay. And then we can also say this one is 1, so 1 can also be considered. So this one is 1, first, second, third, fourth, this one is 1, okay. This is also first, within first, right? So these are the guys who are lying under first standard deviation, okay. So you can see majority are within first standard deviation, as I told you, okay. What is first standard deviation? First standard deviation is 24 plus 5.96 and minus 5.96. This is the standard deviation, right? So if you calculate over it, you will get 24 plus 5.96. It will be equal to 29.96. Okay, almost 30. Okay, and this will be whom? These will be 18 point something 04, right? Okay, so you can see these all values are within first standard deviation. So that means maximum are within first standard deviation. So what we can say, all those guys which are in within first standard deviation will pass. Okay, apart from that, these will also pass because they are having a good marks. Okay, these are in second standard deviation. All these guys who are in second standard deviation can fail. Okay, what we can say these guys which are in second standard deviation in negative side, these are in second standard deviation but these are in negative sides. Okay, these are less in number, so we can say these are within second standard deviation, so they can fail. Okay, and this is the heaviest mark, so this is exception that we can consider. Okay, so that means ultimately the standard score, this is known as what? Standard score. Standard score are used to calculate what? You should understand why it is required, because it will be required at the later stage, the meaning of it. Okay, that's what it is required to figure out the things, or you can say the values which are repeating most often, values repeated most oftenly. Okay, most kind of a most repeated values. Okay, most common value or most likely value. So three categories are there: most likely. So most likely will be always within first standard deviation. That means we'll have a standard score less than 1. Okay, we'll have a standard score between -1 to 1. Okay, if there is a value which is most likely, comes in the most likely category, okay, we'll have a standard score between -1 to 1. Correct? All those values which are having a standard score between -2 to 2, okay, that means it is greater than, smaller than -2, but sorry, greater than -2 but smaller than 2. Okay, but between this one, this is the range. Okay, these will be enough. First, these are what? Less likely. Okay, less likely. So how many less likely are there? There are two less likely. Okay, these are the two less likely. and third is called least likely, this one, under third standard deviation. That means a standard deviation multiplied by 3. So what is standard deviation? This is first standard deviation. What is second standard deviation? If you multiply this thing with 2, that will be second standard deviation. If you multiply this thing with 3, that will be third standard deviation. So within third standard deviation, the values are least likely. Okay. So what we do generally, we remove all those values which are less likely or least likely. Okay. So that's how we can figure out the nature of the feature, like how our features are basically present, and based upon that we can decide, correct, that which are the important feature, which are not the important feature. Okay. So these are the things that we should know. Okay. After this, we have to understand what? We have to understand something that is known as, just a minute, let me remove it. Covariance. Okay. So we have seen what? Mean, variance. Okay. We have seen mean, we have seen variance, we have seen standard deviation, and then we have seen standard score. Okay. And slowly we are going for the next concept that is known as covariance. Covariance means what? Variance between different features. Okay. How the features are related to each other. Variance means what? Variance means the relationship between itself, means the variance within. Okay. Variance means what? The variance within. Okay. That means how different features are related to each other, and what are the, what are the kind of standard deviation and all those things. Means finding out the relationship within the features only. Okay. Like which are likely, which are less likely, which are least likely. Correct. Covariance is what? Covariance is like, it is a basically a metric that show how similar the variance of the features are. How similar the variance of the features are. Correct. That means what? Suppose you are having feature 1, feature 2, feature 3. Correct. So it will have some variance. Variance 1. It will have what? Variance 2. Okay. It will have what? Variance 3. Okay. So basically covariance denotes what? Covariance denotes that these variants are how much similar. Okay. The variants which are, these variants are how much similar. Okay. These variants are how much similar. Okay. So if these variants are similar, okay, suppose these variants are similar, okay, in that case what we can say, that the another feature is highly related to first feature. Okay. That means suppose there are two features, f1 and f2. It will be like this, f1 and f2. Okay. And their variants are very similar to each other. That means it means that instead of using both the feature, we can use single one also, right? That means their information, you can say, we will not lose like kind of the information is the same information they are basically representing. Okay. What we can say, we can say that same information both of them are representing, so that is called covariance. Okay. So what we try to figure out, okay, the features with highest variance difference, highest covariance. Okay. That means suppose these two are having a covariance high, like having a high covariance as compared to this one. Okay. That means these two are having a huge information as compared to these two. That means if I can consider these two, okay, these two covariance are high. Covariance means what? That means relation between variance. Okay. So if there is a huge difference between the variance between this one and this one, huge difference between the variance between this one and this one, that means these two are having separately, these two basically separately, what you can say, containing, okay, containing huge information as compared to these two, because their variances are high. Correct. So this is called your covariance. Okay. So how can you calculate it? Let me tell you. You can calculate it like this. It will be like this. Let's see. Okay. Okay. Let me tell you like this. Suppose we are having a kind of, like we are having a data x, in which we are having three features, x1, x2, and x3. Correct. Then what we can do, we can calculate the variance of them like this. Okay. This is the variance of x1. This is a variance of x2, and this is a variance of x3. Okay. Now we have to figure out how these variants are related to each other. Then what we can do? Okay, what we can do with that is to figure out how these variants are related to each other. Obviously, what we can do this thing. We can just calculate this thing XTX. What is XT? It is transpose. Okay, it is what? It is a transpose. This is one matrix. Okay, this is what? This is one matrix. So if you can transpose, you can get the value. Correct? That means what we can do like this. X1, this is a transpose, X2 and X3. Correct? Okay, and then transpose the actual value. X1, X2, X3. So if we calculate this dot product, what we can figure out? We can figure out the similarity or dissimilarity between the features. Isn't it? Similarity or dissimilarity. Like how the features are similar and how the features are dissimilar. Isn't it? This we can calculate over here. Right? That means what? It will be like this. If you write it, you can write this thing like this. There is a matrix generated. Okay, it is what? It is 3 cross 1. This is what? This is 3 cross. This is 1 cross 3. Okay, that means what will we get? We will get 3 cross 3 matrix. Correct. That means it will be like this. Dot product of x1 into x2. Correct. Please try to understand it. Very important. Like how actually the features decreased. What are the procedures that we have to follow? Dot into x1 into, sorry, I just made a mistake. Dot into x1 will be there, right? Okay, then dot product of x1 into x2 plus dot product of x1 into x3. Correct? Better? Then over here dot product of x2 into x1, then dot product of x2 into x2. Okay, then dot product of dot of x2 into x3. Okay, this is how. Okay, and x1, x2, x3, x3 are what? These are the variances. Variance of x1, you can say. I should write vx1. Okay, vx1, vx2. Okay, variances. Variance, you know what is variance, right? Variance representing the complete. Through with the help of variance, we calculate standard deviations. Okay, so it is what? X3 upon x1. Variance represents the information. Okay, x3, x2 dot x3, x3. Okay, x3, right? What is variance? Variance basically, if you are having any value x1, x2, x3. Okay, sorry, x1 I'm not using because again you get confused. Suppose you are having a value k1 features, k1, k2, k3, k4, k5. Okay, then there is k bar. Okay, so k1 minus k bar whole square plus k2 minus k bar whole square plus, okay, k5 minus k bar whole square divided by 5. Okay, that means it represents the, you can say that how the value is distributed with respect to mean. Okay, the distribution of value with respect to mean. That means how the values are distributed from the mean. This is what represented by variance. So this is the column representing the variance of first feature, variance of second feature, variance of third feature. Okay, now we are trying to figure out how these variances are related to each other. Okay, how these variances are related to each other, and to calculate covariance, what we are doing, we are using this particular thing. Okay, we are using this particular thing, right? So what we are getting over here, we are getting the things over here, that is variance of feature x1. Okay, what is this? This is the variance of feature x1. Correct? Sorry, if we have to calculate, okay, if you have to calculate the variance, then what you have to do, just let me make a small change. You have to divide this thing by n. Okay, because ultimately it is divided by n. Okay, so you have to divide by n. It is divided by n. Correct? Everything divided by n. Now if you see over here what we are having, this will be considered what? This will be considered as variance of x1. Okay, and at the same time, because both side x1 is there. Okay, and if you consider this, what you will get? X1 and x2. So it is a covariance basically. Covariance of x1 and x2. right? So what covariance of x1 and x2 is will repeat it will represent the similarity of change. Okay, it will represent the similarity, or you can represent the changes, okay, like of ith and jth feature. Okay, that means of the first feature with respect to second feature. Okay, like how the first feature is changing with respect to second feature. Okay, that's what it will represent. That's what it will represent. Okay, that means how the feature, if the variance value is low, okay, if the covariance value is low, that means it is not so much related to each other. Okay, that means it is very much similar. If the variance value is low, it is very much similar. Okay, both the features are very much similar, correct, because variances are low. Okay, because the dot product that we calculated, it will represent the same thing. Okay, with the dot product in a matrix, we can figure out like how the things are related to each other, correct. So that means if the variance is low or if the covariance is low, that means it is having very much similarity, right? And if the covariance is high, that means it is having a very high dissimilarity. Okay, if the covariance is high, that means it will have a very high dissimilarity, right? So if we want to understand it, what we can do, we can just take a small example. Okay, so let me take a small example. Okay, let me take a small example over here. Okay, so suppose there are two stocks. Okay, this is return of a stock A. Okay, and there is a stock B, so this is return of B. There are two stocks we are having, stock A and stock B. Okay, now stock A is returning at a rate of 1.1%. Okay, for any quarter, then 1.7%, then 2.1%. Okay, then 1.4%, then 0.2%. This is the return of A. Okay, this is a return of B, 3.0, 4.3.0%, 4.2%. Okay, 4.9%. Okay, 4.1%, and 2.5%. Correct. Now, if we have to use dimensionality reduction, if we have to use PCA, we should know how the features are related to each other. If we are not knowing that how the features are related to each other, obviously we can't reduce the number of features. Can we reduce the number of features? We can't reduce the number of features. Correct. If we are not knowing how the features are related to each other, we can't reduce the number of features. Right. So who will tell us that how the features are related to each other? This covariance thing will tell us how the features are related to each other. So let's calculate the covariance between these two features. Okay. So to calculate it, we have to calculate the mean of A first. So what is the mean of A? If you can calculate, you will get around 1.30. Okay. You will get what? 1.30. This will be the mean of A. What is the mean of B? If you calculate, you will get around 3.74. This you can calculate and you will get. Correct. So you are getting a mean of A as well as you are getting a mean of B. Now question is, why we should use mean of A and mean of B, right? We have to calculate the mean of A and mean of B because we have to calculate the covariance, right? So covariance is what? Is basically a dot product of those variances, right? Dot product of those variances, right? So what we can do, what will the variances? It will be 1.1 minus 1.30. Sorry, 1.30. I just made 3.30. Correct. Okay, okay, multiplied by, okay, multiplied by what? The B, the variance of B. What is variance of B? 3.0 minus 3.74. Okay, this will what happen ultimately if you do the dot product. This is what you will get. Correct. And then what you can do, you can just take this thing as it is, thereafter plus, right? This will be what happen, right? Like for example, if you are having this thing, okay, this is your variance of X, variance of A, this is your variance of B, correct? and this is your variance of A, this is your variance of B, right? So what will you will get? You'll get this thing, covariance of A with A. Okay, so with A it will always be same, that means 1. Covariance of A with respect to B, okay, covariance of A, covariance of B with respect to A, and covariance of B with respect to B. This is what will be calculated. Here what we are doing, we are calculating this thing, covariance of A with respect to B, correct? So if you are doing this thing, so that means what we will do, we'll multiply this thing with this one, correct? So the same thing I am doing. So covariance of A this one, covariance of B is this one, correct? Now this will be done for everything, right? So this is this one. Now we do for the second one, second value will be what? 1.7 minus 1.3 multiplied by 4.2 minus 3.74, right? Plus 2.1 minus 1.3 multiplied by 4.9 minus 3.74. You can calculate it, right? And this will be continued till last. Okay, divided by what? Divided by 5. This will be equal to 2.66 divided by 5. If we calculate it, 0.53. It means what? It means A and B is related to each other. It's somewhat related to each other. It's the variance are dependent. That means A, whenever A is true, that means A is positive. The covariance calculated is actually a positive value over here. Okay, what it indicates? It basically indicates that both the returns are in same direction. Okay, both the returns are in same direction. When A is having a high return, B is also having a high return. Ultimate result. Okay, that means A and B are basically having a huge variance between them. So both the informations are basically important and all, right? So that's how we can decide the covariance. Now question over here is why we are calculating this covariance and all. That is very important. Now we'll come to the like conclusion of our discussion, right? We have to conclude our discussion and we have to decide like why we are using this particular thing, covariance and all, correct? So let's see. Just a minute. Just give me 1 minute. Okay, so let's see how it can be done. So to do it, next we have to understand the PCA concept. So I hope you understood the covariance and all, right? Yeah, right. Just like precision. Yeah, you are on a right thing. Okay. Now understand the PCA, how it is used. Look here. PCA means principal component analysis. Okay. So what we do in PCA actually, in the PCA, I'm just giving you the initial concept of PCA, and later on we'll see how covariance is used over here. Okay. Suppose I am having two feature 1 and feature 2, correct? These are the two features. Two features. Now what I want to use a single feature in place of f1 and f2. Then what I will do, I will try to figure out a line. Okay, I will try to figure out a line over here and will project all the points over it. Okay, and we'll project all the points over it. what I'll do, I'll try to figure out a line over here, and what I will do, I'll project all the points over it. Project, data projection, point projection, okay, in coordinate geometry. Okay, so over here, what are you doing? We're just projecting all the points over it. Correct. So when we projected the points over it, okay, the condition will be like that. What will be the condition? The condition is, after projecting the points over it, correct, the variance should be maximum. Variance should be maximum. Variance should be maximum on what? This variance. Okay, because it is getting projected over here. Okay, like suppose initial points are what? These are initial point x1, x2, x3, x4, x5, x6, x7, x8, and x9. Okay, so x1 to x9 we are having different points. It is very actually it is so much like we generally get so much confused with it, but I'm trying to explain in a very simple way. Still, if you're having any doubt, please do let me know, right? I will try to explain again, right? So we are having x9, so this must have certain variance, certain xv, you can say. Correct. Now what are we doing? We are transforming means what? We are just projecting all these points over these lines, over this line. Okay, now this kind of line can be, there can be n number of line can be there. Okay, this is also a line, this is also a line, then why only this line? Because after projecting on this line, what is the condition? The condition is, out of all the options, this line is giving us the maximum variance. Maximum variance means what? Maximum information gets stored. That means we are not losing information. What is the variance over here? This is the variance. You can see it is a difference. Okay, the maximum, the difference between these points, okay, these projected points, the maximum the variance, isn't it? The maximum the difference between these points, the maximum the variance, isn't it? If the differences are more, the variances will be more, right? Like you can say, here is a, there will be, these points are projected. Now after projecting, it is what? xp1, xp2, xp3, okay, xp9. Okay, so it is what? Again the variance will be there, but this time the variance will be what? The variances of projected points. Okay, the variance of projected points. If this value is high, right, that means what? That means after projecting also we ensured that our information is stored. We didn't lose information. That is important, because after projecting it may happen that there can be a condition like 2 points gets projected on the same point. Okay, like 1 point from this side, another point from this side. From this side 1 point is getting projected, and other point from this side getting projected, and they all projected on the same point. Okay, so if those 2 points will get projected on the same point, then what will happen? We'll lose the information, isn't it? Because these 2 points will be represented, because these 2 points are different points. Okay, so these are representing different informations, but when they projected over here, now they will be represented by a single point. Okay, so obviously we lose the information, right? So that's why with the different line options, we choose that particular line where the variance is maximum. Okay, because maximum variance means what? Maximum value is stored, restored, right? That means what? Just consider a case. Suppose over here I am choosing another line. Just suppose I choose this line. Okay, I choose this line. Now again I am projecting over it. I projected this point over here, and I projected this point over here. Okay, I projected this point over here, I projected this point over here. Okay, I projected this point over here, I projected this point over here, I projected this point over here, and this one is also projected, and some other points are also there. This one is also there, this one is also projected. So you can easily see that over this, these points are basically overlapped. Okay, so that means we lose certain information. Obviously we will definitely lose information. It is not like that we can't, after projecting, we can't make sure that 100% information is secured. Okay, we will definitely lose information, but we have to make sure that we are losing as less as possible. Getting a point? We have to lose as less as possible. And how is it possible that we can make sure that we are losing as less as possible? If the variances are more. Okay, so in this case, you can see the variance is less. This is the complete variance range. It is less. And in the older case, this is the variance. It is more. Variance is more. That's why this line will be considered for projecting the points. This line will be considered for what? For projecting the points. You're getting my point? Okay, I will tell you how this line we are going to find, that I will tell you. Okay, how we are going to figure out this line, that definitely I'll tell you. But first of all, let me tell you that you should understand which line we have to choose. We have to choose that line where the variance is maximum after projecting all the points, because after projecting only this f1 and f2 can be converted into one feature called fx, because after it will be projected it will be on a single line, and when it is on a single line we can consider the equation of this line. Okay, when it is projected on a single line, what we can do, we can consider the equation of this line, y hat is equal to ax plus b, something like this. Correct. And based upon the equation of line we can figure out the values and all, right? So this equation can tell you a simple one thing, that is a simple one feature. Okay, that means instead of using two features, we are just projected a point over here, and that projected point we are now considering as a single feature. Okay, that projected point what we are considering as a single feature. Okay, actually the projected point is not considered. I will tell you what actually get considered, but first of all let me tell, first of all just make me tell me, is it clear or not that which line to be considered and where to project? Please just tell me. Okay, that's great. Okay, fine. Okay, so let's proceed for the next part. Okay, so this was what we had discussed. Okay, now we have to discuss the projection. What is point projection, right? So let me tell you about the point projection. So point projection we had studied actually, so little bit things we might have missed, but nothing to worry. Once I will tell you, you can easily you will memorize those things back. Okay, if you missed it, because all of these things we have already studied, but we had studied in class 10th, 12th, and kind of before graduation. So some points we may have missed. So let me tell you about the, and many of, if you are from the mathematical background, you must be knowing also. Okay, so if this is your line, right? Suppose this is your line. Okay, this line will be represented by some vector v. Okay, this line will be represented by some vector v, and this is a vector x. That means it is some point. Okay, and now we have to project it. So how can we project it? The projection will always be at 90 degree. Okay, that is, we know. Okay, the projection will always be at 90 degree. Okay, so this projected vector will be represented by what? We know it will be represented by x minus projection of x over L. Projection of x over L. What is L? This one is L. I am considering this thing as a L. This is line L. This vector v is basically unit vector of this line L. Vector v is what? It is a unit vector of this line L, right? L is not a vector, otherwise L and this one, L is not a vector. Basically L is just a representation of line, otherwise L and v will remain same. Okay, v is what? V is a vector representing the direction of line L. Okay, x is another point, okay, represented by a vector x. X projected over L, so this particular thing is represented by x minus projection of xl. Okay, now it is what? Okay, it is what? Basically this is known as projection of x over L. Okay, projection of x over this, only this much. Okay, this is your projection of x over L and all those things, right? So no, this complete thing will be known as, why I'm saying only this one. Okay, fine. So this is a projection of x over L, right? Now what I have to do, I have to represent. Okay, then what is L? L will be your, L is equal to CV. Okay, what is CV? Where C is nothing, it is just a real number. Okay, it is just a real number. Correct, it is just a real number. C is what? C is just a real number. Okay, any value, right? So basically what happened, L is what? L is CV. This is your projection of x over L. So what we can say? We can say projection of x over L will be called as C of V. Okay, correct. This is what I can write. Okay, V is what? V is what? V is just a unit vector. If you multiply the unit vector with C, what will we get? We'll get this thing. Okay, if you multiply a unit vector with any real number C, we'll get this particular length. Correct, which this length is representing what? This length is representing projection of x over L. Correct. Now we know the product of dot product of perpendicular vector is 0. Dot product of perpendicular vector is 0. That means what? That means x minus projection of L over x multiplied by what? Multiplied by v. Only v can be there because vector. Okay. So dot product of two vectors. This is vector 1, this is vector 2. Okay. So dot product of two vector, if they are perpendicularly aligned, this will be equal to 0. Okay. That means x dot v minus projection of, or you can also say over here, okay, you can write this thing like this also, projection of x over L dot v is equal to 0. This can be represented by CV. Okay, so that means x dot v minus CV dot v is equal to 0. Okay, that means what we can say, C is equal to x dot v upon v dot v. This is a unit vector. Okay, this is what? This is just a unit vector. So we can also say x dot v. Okay, x vector dot v vector. That means if I have to calculate the projection of any point, okay, suppose you are having any features, okay, and we are projecting over the line, okay, we are projecting those features over the line, okay, that means what we have to do, we have to just calculate the dot product, okay, the dot product of the vector, we have to just figure out this vector, okay, where the you can say, we have to just figure out what, we have to just figure out the vector where the, you can say, variance is maximum. We have to figure out that particular line, we have to figure out that particular line and vector of that particular line, okay, vector of that particular line where the variance is maximum, and then we have to calculate the dot product of the point with respect to vector, okay, and we will get what, we will get C. C is what? C is the length, okay, C is the length that we are getting, okay, C is the length that we are getting, and basically this C will be used for what, for kind of a, you can say, as a single feature. So C is what? C is basically a scalar projection. C is what? C is basically a scalar projection. Okay, C is a scalar projection. A scalar projection means what? The length. Okay, length of this thing, length of projection. Okay, C is what? C is this length of projection. And if we multiply C with V, the vector. Okay, vector means what? The direction. We will get the vector projection. Okay, vector projection. Vector projection means what? The coordinate of these projecting points, x, y. Okay, the coordinate of the point where the projection is basically made. Okay, the coordinate of the point where the projection is basically made. Okay, so that is called C dot V. But we are not going to use this thing. We are going to use these things only a scalar projection. Why? Because maximum the C value, the maximum the variance. Correct? If the C value is higher, variance is obviously higher, right? That means if suppose there is a line, if you can consider this thing as it, okay, this is the distribution, okay, these are the distribution, right? And on this distribution, if suppose this is a line and all of these gets projected, and we have calculated the value of C for all of these points, okay, and we summed up the value of C, okay, and if, and then the second direction, this is also a direction, okay, where I projected all these things, okay. So in the first case, if the value of C is higher, that means variance is higher, okay. In the second case, if the value of C is lower, that means variance is lower, okay. Then obviously this thing should be considered, okay. So basically this value of C will be considered as the features also. That means if you are having so many points, suppose x1, y1, x2, y2, x3, y3, x4, y4, these are different features, right? Or basically I should see like this, okay, f1, f2, f what I should say, actually features I want to represent, so I can represent like this, f1, these are the features f1, these are the features f2, okay, this represent these features as f1, this is f2, okay. So when we project it, these 2 points, what we will get, we'll get C, okay. So this C, how many C we will get? Suppose you are having a features over here, x1, x2, x3, x4, x5, x6, like this, and over here y1, y2, y3, y4, y5, y6. Obviously, you will get what? C1, C2, C3, C4, C5, C6. Okay. So if these are higher in number with compared to other, that will be the projected point, and this will be considered as the new feature. Okay. This will be considered as a new feature. This will be considered as what? As a new feature. Why? Because they are preserving more information. They are more in length, they are preserving more information. They are representing higher variance. Okay. So that's why these will be the new features. We are not considering vector projection, because if you consider vector projection, what will happen? Again, you will get two coordinates. So what is the benefit of converting two coordinate into two coordinate? There is no benefit. Ultimately, two coordinates gets converted into two coordinate. So there is no benefit of using it, vector projection. Okay, that's why we use what? A scalar projection. We only consider the length where it is getting projected, and with the help of length only, we basically figured out that where the projection is maximum, okay, and where the projection is, sorry, where the variance is maximum and where the variance is minimum. Okay, and the point where variance is maximum, we just consider them as a projected line to be used, right? So better you can take the screenshot of it, because like if this thing will not be written or the screenshot is not there, you may missed it, but I guess you may get a recording of this one also. So I guess you'll get the recording, but in last class you got it. So you can just go through it, because again you have to go through it, okay, because there are so many things. So let me conclude what we covered till now. We first understood mean. With the help of mean, we understood variance. Variance is the difference with respect to mean. Okay, then we calculated the standard deviation, then a standard score, then covariance. Covariance means what? The relationship between different features. Okay, for that we used a example of a stock thing, return of A, return of B. Then we understood the projections. We have to project the points, but we have to project the points over that line where after projecting, okay, not before projecting, where after projecting we are getting a maximum variance. We have to project the points over that line where after projecting we get the maximum variance. Okay, where after projecting what we get the maximum variance. Correct? So this is what we have covered till now. After this we will go for the part of something, one more thing, like what this line is known as. Okay, what we call this line. Okay, that is what we are going to see. Okay, I will take a small break of 5 to 7 minutes, and thereafter I will tell you what this line should be called as. Okay, shall I take a small break?
Okay, sir. Okay.
Okay.
Yes, sir.
Okay, so let's proceed. So we understood certain things. Now we have to understand the projection in detail. Okay, now let's see the problem with the projection. What happens actually with the projections, right? Okay, so what should I do? Okay, okay, so let's consider a vector A, sorry, matrix kind of A, 1 2 2 4. Okay, like 1 to 2 4 is just a matrix, right? So it may represent like this. Okay, 1 comma 2 or 1 to 2 4, some points can be there, 1 2 2 4, like this, some point can be there, right? Okay, just imagine this is your just a minute. Okay, let's do it. Just imagine 1 to 2 4. These are the, suppose this is a matrix representing two features. Okay, like feature 1, just feature 1 and feature 2, right? Feature 1 and feature 2, right? Now you have to project it over a point. Let's consider a particular vector, or you have to project it over a vector, right? Let's consider a vector 1 1. Okay, that means the B will be what? 1 1. That means I have to project these points over it. B 1 1. Okay, over this vector 1 1. Okay, now when I'm projecting it, Okay, then I have to use A dot B. As I told you, we have to use dot product. Correct. Now, if I'm using dot product, what exactly happens? Just see. Magic happens over here. If you do it, you are getting 3, 6. That means complete direction changed. Okay. That means it is what now? If you call it 3, 1, 2, that means it is a vector 1, 2. If you consider a unit vector is 1, 2. Okay. You tried of projecting over 1, 1, right? You tried of projecting over 1, 1, but what happened? That it is changing the direction to 1, 2. Okay. So that is the biggest challenge. That means whenever we will try to project using the dot product, what will happen? The direction will change. Okay, the direction of vector is changing itself. Then how can we kind of how can we solve it out? Look here, for every matrix there is something called eigenvector. Okay, for every matrix there is something called eigenvector. Correct. If you project, if you are calculating a dot product with respect to eigenvector, the direction will never change. Okay, the direction will never change. Okay, that means what? Suppose your A is this one. Okay, and this is B1. Let me consider B2 over here. Okay, and B2 is equal to what? 1 or 2. Okay, now if you project it, okay, if you project it over B2, that means A dot B2, or if you calculate dot product of A and B2, what will you get? You will get 5, 10. Okay, the magnitude may change. This is your value C, and this is your thing. This is C. Okay, you can see we are doing a projection, we are calculating a dot product. Okay, now with the dot product, what are we getting? We are getting this thing. Okay, so you can see the direction is not changing. Okay, only the magnitude increased to 5, 10. Okay, so for every vector there is an eigenvector only. Okay, there is only eigenvector for which direction never change. Okay, there is only what? Eigenvector for which direction never change. Okay, that means we have to project the point where we have to project the points over eigenvector of that particular matrix. Correct. Now, how to calculate the eigenvector and all? Look here. To calculate the eigenvector, we need something called eigenvalue. What is the representation of eigenvector and eigenvalue? It is a representation of eigenvector and eigenvalue. A v is equal to lambda v. Okay, where v is your vector, lambda is your eigenvalue. Okay, v is what? V is your eigenvector. Okay, higher the eigenvalue, higher the variance. Okay, if eigenvalue is higher, we will have a higher variance, right? So how to calculate this thing, this vector and this all thing, these all stuffs? Okay, so what we will do, we'll do a small change. Okay, we will write the same thing like this: AV is equal to lambda identity matrix into V. Okay, I just put identity matrix over here. Okay, now what I will do, I will rewrite this thing like this: AV minus lambda IV is equal to 0. Okay, and the same thing I can write like this: determinant of A minus lambda I is equal to 0. Now calculate the determinant of this thing. If you calculate the determinant of this thing, what is A? A can be any value. Suppose I am just considering a value A as, or you can say determinant of A. So A can be any value that I am considering. Okay, 2.0, 0.8, 0.8, 0.6. Okay, some vector. Okay, minus lambda I 1, 0, 0, 1. Okay, this will be equal to 0, and from here if you calculate the determinant, so determinant will be what? Determinant of 2.0 minus lambda 0.8, 0.8, 0.6 minus lambda is equal to 0. Correct. Now if you calculate determinant, so if you calculate determinant, it will be like this: 2 minus lambda, 0.6 minus lambda multiplied by 0.8 multiplied by 0.8, okay, is equal to 0. Okay, then lambda square is equal to, sorry, lambda square minus 2.6 lambda plus 0.56 is equal to 0. Okay, then if you calculate, lambda will be lambda 1 and lambda 2 will be there. It will be equal to what? 2.36 and 0.23. What it means? It means for this particular vector there are two eigenvalues. Okay, for this particular vector we are having two eigenvalues. Why? Because there are two features. If you are having 10 features, then how many eigenvalues? 10 eigenvalues, correct? If you are having 10 features in a matrix, that means you will arrange all the features in a matrix. This is feature 1, this is feature 2. Okay, the same way if you are having 10 features, okay, if you are having 10 features, then you will have how many eigenvalues? 10 eigenvalues. The first eigenvalue is the highest one. Okay, that means the eigenvector represented by this first eigenvalue, the eigenvector represented by this eigenvalue will have maximum variance because it is highest in value. The second largest, okay, suppose you are having 10 eigenvalues, okay, over lambda 3, lambda 4, lambda 5, suppose 5 eigenvalue, okay, it is your 12. Then we are having suppose something like 10, then you are having eigenvalue suppose 7, then we are having eigenvalue 6, then we are having eigenvalue 2. Okay, then the first eigenvalue, the vector because of first eigenvalue the eigenvector because of first eigenvalue is highest. Okay, that means the vector because of this eigenvalue will represent maximum variance. The vector because of next eigenvalue will represent second highest variance. The vector because of third eigenvalue will represent third highest variance. So instead of using all the vectors, what we can do, we can just use top 3 vectors. Okay, instead of using all the vectors, what we will do, we will use top 3 vectors and we will project all the points over here and over here. As these are eigenvector, direction will not change. If direction will not change, that means our projections will be done. Okay, and thereafter what we can do, we can say that those projected points are our 3 new features. Instead of using all the 5 features, now we are using only 3 features where the eigenvalues are maximum. The maximum the eigenvalue, maximum the variance that we have already seen, right? So that means if you are having 10 features, if you are having 20 features, you will get a matrix of size 20. That means you will get 20 eigenvalues. That means you can get 20 eigenvectors. Let's consider the eigenvectors over here. Okay, let's calculate the eigenvector over here. So how can we calculate the eigenvector? Let's see. Calculate the eigenvector. What are our eigenvalues? Our eigenvalues we have calculated. So based upon this particular equation, this is our A to 0.8, 0.8, 0.6. Okay, V1, 1, V1, 2. Okay, is equal to eigenvalue, first eigenvalue 2.36. V11, V12. This is what we have to calculate, right? So to calculate it, let's rewrite the equation. It will be what? 2 V11 plus 0.8 V12 is equal to 2.36 V11. This is what? 0.8 V11 plus 0.6 V12 is equal to 2.36 V12. Two equations, two unknown. Okay, two equations, two unknown can be easily calculated. V1 is equal to 2.2 V12. That means V11, or you can say V1 vector 1 is equal to 2.21. So this is your first unit vector representing first eigenvector. The same way you can calculate the second eigenvector with the help of 0.323. That means all these points, okay, if you project over here, the direction will not change. Okay, and we can project all these points over this thing so that we can get the less number of features. Okay, we have to project all these points over this line. We can get a variance of 2.36. That is our eigenvalue. Eigenvalue represents the variance. Okay, so this is how you can make the projections and can make the decisions, right? So just see in practically how we can do it. So that means what? If we are having any feature matrix, we have to first calculate the you can say the covariance of it. Okay, based upon the covariance, okay, eigenvectors and eigenvalue will be calculated, and thereafter rest of the things will be done. Okay, so let's do it practically and see how we can do it. Okay, so to do it practically, what we will do, we will first pick. Why are we choosing eigenvector? Because over the eigenvector, if I will do a matrix multiplication or dot product using eigenvector, the direction will never change. Only magnitude will change. Okay, only magnitude will change. So for a matrix, we have to only project over eigenvector. Okay, we have to only project over what? Eigenvector by using the dot product. Okay, call collab. Unsupervised PC, principal component analysis, right? So just import numpy as np. Okay, for calculating eigenvector, okay, fine. Now define a array. A is equal to np dot array 6, 5, 2, 3, 1, 4. So these are what? These are our these things, matrices. Okay. Step 1 was what? Calculate the mean. Okay. For the variance and all, so calculate the mean of each column. Okay. So how to calculate? M is equal to mean of what? Each column. So if I will give mean of A, so let me see. Print. Yeah. Oh, okay, fine. It's np dot mean. I'm sorry. Okay, it's a mean of everything. I have to give the axis. Axis is equal to 1. Yeah, fine. Now axis equal to 0. Sorry. Okay. So mean of each thing, right? 6 to 1. The mean of 6 to 1 is what? 6 plus 2 plus 1. That's 3 divided by 3. It is 3. 5 plus 3 plus 4. It is what? 12. 12 divided by 3 is 4. Okay. So mean is calculated. Then we have to calculate the variance, and also for variance we have to calculate the subtract the things from the mean. Okay. That means subtracting column value by mean, because you have to calculate variance and all, right? So it will be what? C is equal to A minus mean. Okay, so print C. Okay, so this is done. Okay, thereafter calculate covariance now. Okay, so once it is done, thereafter you have to calculate the covariance, because I told you how to calculate covariance. After we calculate to calculate the covariance, it was what? We have to calculate the variances and all, and this is what the variance. This is how for calculating the variance we have to subtract from the mean. Okay, so we have subtracted from the mean. Now we can calculate the covariances. Covariance between different features, between two features, right? So for the covariance, calculate the covariance matrix of centered. I'm calling the previous matrix as a centered matrix because that is in the centered, okay, or of mean matrix. Matrix using mean matrix. So what that will be? That will be your V is equal to covariance np dot cov, covariance function is there, C. Okay, print V. Okay, I just did a mistake. It should be dot T. I should do dot transpose of it should be considered. Yeah, that's fine now. Okay, dot transpose. Okay, we have to pass the transpose of it, then only it will calculate. Okay, so it is how it's done, right? So how it is getting done? It is multiplying. It is making this thing like this. Just a minute, I will tell you how it is calculating it. It is calculating like this: 3 minus 1 minus 2 1 minus 1 0. Okay, and then 3 minus 1 minus 2 1 minus 1 0. Okay, so 2 cross 3 3 cross 2 2 cross 2. If you are having a 2 features, you will always get 2 cross 2. If you are having 3 features, you will get 3 cross 3. If you are having 10 features, you will get 10 cross 10. Okay, so according to the things, you will get it. Okay, whatever the things are there, right? So this is what that I am getting calculated. Okay, the covariance between the things, covariance of feature 1 with 1, covariance of feature 1 with 2, covariance of feature 2 with 1, for covariance of feature 2 with 2. Okay, now you have to calculate the eigenvector and eigenvalues, right? So eigen decomposition of covariance matrix. Okay, it will be what? It will be values comma vectors okay, is equal to np dot lin lg dot aigp. Okay, print values and print vectors. Okay, so these are our eigenvectors and they just mix. So print. So first one is your eigenvectors, eigenvalue. Second is your eigenvector. Okay, so these are eigenvalue. Eigenvalue representing the first highest eigenvalue. That means this, if the projection will be done on this thing. Okay, so this is your kind of a maximum thing. Okay, and this is the second eigenvector. This is your first eigenvector. This is second eigenvector. Okay, so what we can do, we can project the points over these eigenvectors, right? So how can you project? We can project the point over these eigenvector by that thing. We are having a data points. Okay, so what is your projected points? Project data. Okay, so what we can do, we can just use dot product. So np dot okay, dot what? The centered value. Okay, the centered value we can project, that is c dot c comma vectors. Okay, so these are the projected points. Okay, these are what? These are your projected points. Okay, so these are what we can say, p is equal to this one. This is your projected points. Okay, that means these are the projected point. That means if we have to consider a less number of feature for 2 1, we can consider this one. This is representing those two features with a highest variance. Variance what? 7.60. Okay, and this is representing second feature. Correct. If I have to do it using the library, that also we can do. Okay, PCA using library. Okay, so let's see how we can do it library using library. That is very simple actually. Let me define these things again. Okay, we have to call what? We have to call from sklearn dot decomposition import PCA. Okay, and then I have to define how many components I want. So PCA is equal to PCA. I want 2 components, so just give 2. Okay, and thereafter fit your data. PCA dot fit A, correct, and thereafter to get the eigenvalues, access values and vectors, print PCA dot components, sorry, print PCA dot explained variances. Okay. And thereafter transform it. So for transforming, B is equal to PCA dot transform. It will do the projection. VARA variance. Just a minute. Okay. So these are what that we are getting almost the same thing. You can see 7.60, 0.39, same we got over here. Okay. Then these are your things. Only the negative positive might be up down. So that is the thing that can be ignored. So over here you can see the, because you consider vectors and all. So we are having the points representing the projected points. So this here you can use the library. Okay. Okay. So it is how we can do the PCA transformation. Now we can use this particular concept for some real, for some actual data. Okay. So let's see how it is behaving on actual data. Right. So for that we need a data set, right? So let's see. Okay. PCA on real data set. Okay. So we are having let me call a data set from the scikit-learn itself. Okay, scikit-learn is having a very good data set called like from sklearn. We can use a classification based data set over here. Okay, dot data sets import. There's a data called breast cancer data. So that is a classification based data. I don't know like I have used or not. Breast cancer, right? So this is a data that I am calling DF is equal to, in this thing there are 2 types of cancer tumor actually. Okay, so this data is representing those 2 types of cancer tumor. You may have used this data because this is very popular data actually, right? DF. Okay, so you can see this data is basically present in the form of dictionary. It is within the library only. Okay, so this data is representing what? It is representing certain things. You can call this thing as df.keys. So when you call all the keys, what are we getting? We are getting these things. Okay, data, target name, description, feature names, and file name. Okay, so data is important. If I want data, then I can use data only. This is my data. Okay, so this is having so much value. How many values are there that we can access from the feature names? Okay, so how many features are there that you can see over here? Okay, so length of feature, you can just print it. Print length of so how many features are there? Total 30 features are there. Okay, so if we reduce the number of 30, like it is total 30 features, and we just want to reduce it and see the effect actually, how it is behaving. Okay, is the accuracy decreases for building a model when you are building a model, or is the accuracy increases? Right, this is what we have to do over here. Correct. And then we can see a target. What is a target over here? You can see df target. Okay, and target names also. Okay, so these are target 0 and 1. Okay, and target names are malignant and benign. That means only there are two types of tumor, malignant and benign. So these 30 features in a combined way, okay, these 30 features in a combined way representing only two labels, either malignant tumor or the benign tumor, right? So let's do one thing. Just separate your features and labels. So it is your x is equal to and y is equal to. Okay, x will be what? Df data, and this one is equal to df target. Much better. So x and y is defined. Then what we can do? We can split it. Correct. So let's split it for training and testing purpose. Right. So from sklearn dot model selection import train test split. Okay, then x train comma x test comma y train, just a minute, comma y test. Okay, this will be equal to what? Train test split x comma y. Better. And then what we can do, we can call PCA now from sklearn dot decomposition import PCA. Better. Okay, then PCA is equal to, okay, I want to convert the 30 features into two features, so just give two over here. Okay, and thereafter PCA dot fit, what I can fit? I can fit x train. Okay, and thereafter what I am doing, I have to, after fitting, print PCA dot and number of components. Okay, what are the number of components? What are the components that I want to see, that we can see over here? Okay, and then what I can do, I can get the transform it. Okay, so for transforming we are doing what? PCA dot transform. After fitting, transform, that means converting. Okay, PCA dot fit will give you, will calculate all the eigenvectors and all, and then transform will project all those things over that. Okay, so transform is x train, right, and this will be xtr. Okay, and then what we can do, we can print the variance as well if you want. Okay, variance, explained variance, PCA dot explained variance, right? We can just give a print. Okay, so this is done. Okay, some error it is from sklearn dot decomposition, not composition, I'm sorry. Okay, so you can see over here, what are you getting? Number of components is 2. Okay, and these are the explained variance. This explained variance is representing what? Is representing your eigen values. You want to see eigen vector, that means the actual things, and also that also you can see. Okay, but again it will cover a lot of things, right? Now these are the two things that we got. Okay, thereafter we have to see like how my model is performing. Okay, so to see, what I will do, I will call from sklearn dot, just a minute, from sklearn dot neighbors import k neighbors classifier. Okay, and then k model, I'm using knn model over here, k neighbors classifier, anything I can use, but I'm just using it, there is no reason for it. Okay, and then k model. Okay, I will define two k model. Okay, one is without pca and one is with pca. Okay, so for without pca it will be what? K model no pca, np no pca. Okay, and then k model underscore pca, that is underscore p for the pca, one more k model. Okay, so I'm defining two model over here. Let me define two model, right? So without pca, the it will be trained over k model underscore np, it will be trained over x train and y train, right? X train comma y train. Okay, and with pca it will be trained over without pca, that means over all the 30 features. Okay, and this is with pca, with pca, this will be with only two features, right? So k model underscore p dot fit. Okay, what? xtr, that is your reduced component that you can see over here, this is your xtr dot transform xtr, and label is what? Y train, right? There. So this is trained now. Okay, now you have to calculate the accuracy. First of all, let me calculate the training accuracy. Later on we'll calculate testing accuracy. So training accuracy in both the case, training accuracy in both the case will be what? K model with no pca, no p dot score. Okay, x train comma y train, right? And then we are having k model with pca, so it will be underscore p dot score. Okay, so this is a training accuracy. Okay, okay, for training accuracy it should be xtr, right? Okay, so it is almost close. You can see there is a model that is trained over 30 feature, and there is a model which is trained over just 2 feature. Okay, but both are giving us the same accuracy. Okay, so if both are giving us the same accuracy, so that means what? It is never a kind of a wise decision to use all the 30 features for the training data. Let's move for the testing data. Okay, so testing accuracy. So for the testing accuracy, without any PCA, we can directly use print k model dot k model underscore np for the no PCA model dot score x test comma y test. Okay, but you know, for the PCA model we can't use directly like this. Okay, we have to do what? XTS, we have to transform first. Okay, so how to transform? We can transform like this: PCA dot transform, that is already there, dot transform what? X test. Okay, so X test will be transformed first, will be converted into two number of features, because by default X test is having what? 30 number of features, right? It will be transformed first, and thereafter accuracy will be calculated, because accuracy means what? You are predicting. So prediction can be done only that kind of data which is used for training. So for training we use two features. So for testing also you have to convert 30 features into two features. Okay, it is converted, That means whenever a user is coming, okay, and user is giving you any data for prediction, and you trained your model after PCA, okay, like there's a user, he wants a prediction over his data, and you trained your model using PCA, then first of all, you have to transform his data. You have to transform his data into less number of features, and then you have to do it. Okay. So testing accuracy is what? Testing accuracy is almost same. Okay. If you increase it, suppose over here I am using 3 features. Suppose I made it 2, I was using. Suppose I made it 3. Then that will also be covered up. Okay. You can see now 3 eigenvalue. That means 3 eigenvector. Then it will fit. Okay. With, you can see almost same. For training and for testing, almost same. So that means we can say that PCA is working quite good over here. Okay, as well as we want a projection, we want a plot, that also we will do. Let's plot it. Import matplotlib dot pyplot as plt. Okay, plt dot scatter. What you can scatter? XTR for the training set. Okay, training set is having how many features? Just see. XTR. This is your XTR. It is having 3 features now, because 30 features has been reduced to 3 features. Again, these 3 features are getting used, okay, after projection with maximum variance. Okay, the first column you want, so what you can do over here, all the rows in column number 0. Okay, and then XTR, all rows in column number 1, and then color will depends upon what? The label. Where is label? Label is present in white train. Okay, label is present in white train. Okay, and then plt dot so because in the white train we are having 2 labels, 0 and 1, so we will get 2 different colors. Okay, xy of same size, thing changed. Oh, sorry, comma I had not given over here. Okay, so you can see it is, if I am using first top 2 feature, things are well separated. That's why we are getting a good accuracy. After the PCA, if I am using top 2 features, this is what it is well separated, right? That's why I am getting a good accuracy. Correct. That means the information we didn't lose. With the plotting, we can say that the information we didn't lose, right? For the first 2 feature. Okay. Okay, and this is what I'm going for the XTS. Oh, okay, AICTE test. For the testing data also, you can see information it is well divided. That's why you're getting a good accuracy, right? For the testing data, for the training data. Okay, if you're considering for instead of first 2, let me consider the last 2, that is 1 and 2. Okay, you can see it mixed. That's why it is said that the first feature is containing maximum information, second feature is containing next maximum information, and third feature is containing like less maximum information than the second one. Okay, so that's why if second and third is used, it is like that. There is only 3, so fourth I can't use. If I use the first and the last, then something better I will get. Okay, so here also, that means first is important. That's why using first 2 we are getting a good accuracy, but using the first 3 we are getting a best accuracy. Okay, it doesn't mean that you can use the first 4 also, first 5. You can continue, you can use that all 30 feature, because after PCA also you can generate 30 feature. But again, using a more number of feature will not help you, because the accuracy will not change, because maximum accuracy with all the number of feature is this one only. So if you already achieved maximum accuracy, then there is no point of increasing the number of feature. You can make it 4 also, you can make it 5 also, but it will not help anyway. So why to increase? Okay, even 2 is maximum, 2 is enough, but here just for precaution we are using 3. Okay, and we are getting this well separated things. That means information is not lost. If we have to figure out what is the information, basically what we can do, we can calculate it like this: print PCA dot explained variance ratio. Okay, it is saying what? that the first feature is containing 98% of all the information. Okay, 98% of all the 30 features. If you are using all the 30 features, in place of all the 30 features, if you are using only this 98, only first feature, okay, then also it is 98% information it is containing. Okay, you want to see, just a minute, let me use just one feature. Second is containing around how much, around 0.1%, okay, or 1% of information, okay, 1%, and the last one is containing very less information. Okay, so if I will use just one, then what will happen? Okay, just one I'm using now. So you can see, if all the 30 I'm using, I'm getting accuracy 95%. With just one, I'm getting 93%. There is no such a big change. Okay, this is just one feature. Okay, plotting can't be done now because we are not having two things, so plotting we can't do over here. Let me check if I can do with a single one. I don't think I can do, right? At least two dimensions are required. The plotting is not, we can't do the plotting now, right? Anyway, variance ratio you can definitely calculate. So even one is enough. Okay, so it's quite helpful for any system if you reduce the size of feature. It is quite helpful for any system if you can reduce the size of feature like this. Okay, so let me share the code with you. So this is the code. Anything? Okay, so I've shared the code. You can just access it. Just try with different data. Really, PCA is a very good tool. Yeah, right. If we can take a snap, then it will be good, right? I can just keep this thing with me. It was a very good session with you, right? So you can just access it. Try to use this thing with different data sets. Okay, because we are trying to decrease the decrease the size of data with PCA without losing the information. Okay, without losing any information, we are trying to decrease the data, right? So this is really very nice approach that we can apply, right? So if it will be comfortable for you, then it's okay. If it is comfortable for you, then only we can you can make our camera on. If not, then nothing to really, like you. I can understand at home, like people are sitting as it is, right? So if it will be comfortable, then we can make a take a snap. Let me use it for the two. Is it clear?
Sir, turn off the share.
Yes, sir. Yeah, right. It's right. I got it. Just a minute, sir. I guess very few people are making that. Yeah, right.
Actually, all participants are joining from home, so that's why most of the participants are not comfortable. No problem.
Right. I can understand. Right. I can understand, sir.
Right. Okay, those who have possible, no problem. Okay, other way we will take it again tomorrow, no problem.
Right. Just a minute, sir.
Yeah. Just we will wait for 2 minutes. Just those who will turn on, and means it will be better for us. No problem.
Right. I'm also sitting as it is actually.
Zope sir, very good evening.
Good evening, sir. I think this will these are the enough participants. Okay, no problem.
Right, sir. So thank you everyone for being with me during this session. Okay, if anything that because so many things need to be explained, I can understand sometimes we do make a mistakes also. So I also made some mistakes. So just pardon me for that, and we are all improving. So we'll again meet in hope in next year. Happy New Year to all of you, and Merry Christmas as well.
Yeah. Thank you, all the participants.
Thanks
For
a lot,
turning
sir.
on the camera. No problem.
Okay, thanks a lot, sir. Thank you for this snap. Thank you, everyone. Take care. Okay. Shall I sign off?
Okay, sir, no problem. Thank you very much. Okay,
Thank
I
you.
hope everyone has cleared his doubts. So it will be better. And this is today's your last day, sir. No problem. We
Right.
will very much thankful to you, sir, on the behalf of SSBT CVT Bambhori. You have given a nice explanation about these today's sessions, as well as you have given a lot of hands-on all these things. So I hope everyone will try to implement in their research as well as in their PG as well as UGs also.
Right.
Actually, these things are already already put it in their curriculums. Okay,
Right,
so most
sir.
of the faculty are including these machine learning and pattern recognition, artificial intelligence in their curriculum. So that's why this hands-on session will be helpful for them for doing the practicals. So
Right.
thank you very much, Bipul sir.
Right. I'm giving a link where I have written some articles, so that will help a lot if you will go through it. Just a minute, I'm giving a link to everyone.
Right.
Okay.
Sir, I think it will be better for me to you send it to me personally. So I will share it all the participants.
Definitely, sir. I will share it with you, sir.
Right, sir.
Okay.
Okay. Thank you very much.
Thank you, sir.
Right, sir. Okay, then all the participants will meet tomorrow in the morning at near about 9:30. 9:30. There is a first session. Miss Susmita Vasishtha will take the session, and then we will go for second and third session. Tomorrow we have a valedictory function at 2 p.m. Most of the time means in that valedictory session. AICTE faculty coordinator will be present, as well as IST representative will be there. So that's why they have given time to time of their presence in our valedictory function. So that's why we have to revise. We need to revise that schedule for tomorrow. So that's why please follow the schedule for tomorrow. So I will be very thankful to you. So now it is a time to break the end or end the session. So please rejoin tomorrow. No problem. Thank you.